The extended length of the Ulysses mission allowed the Sun to be monitored during periods of minimum and maximum solar activity. It was data from this mission that showed that the polarity reversal of the Sun's magnetic field carried into the heliosphere by the solar wind was a surprisingly simple process. It simply appears to rotate through 180 degrees from sunspot minimum through sunspot maximum and back to sunspot minimum again. Ulysses explored the solar wind from all angles, producing the first three-dimensional view of it in the heliosphere, and monitored how it changed with time. Prior to Ulysses, solar wind measurements were only available from satellites located close to the Sun's equatorial plane. These measurements were assumed to represent the dominant state of the wind. Ulysses showed that a faster solar wind flow, originating at high latitudes, dominates the heliosphere for most of the solar activity cycle. Astronomical observations suggest that the Sun is currently moving through a warm cloud of interstellar dust and gas. Ulysses was able to make the first direct measurements of the dust and helium from this local cloud that has penetrated deep into the heliosphere. Before Ulysses was launched, it was thought that charged energetic particles created during solar storms would be confined to latitudes close to the location of the storms. Charged particles are constrained to move along magnetic field lines, and the heliospheric magnetic field was not expected to have large excursions in latitude. However, Ulysses observed large numbers of energetic particles over the solar poles, far away from the location of the solar storms that created them. This discovery has forced scientists to revisit their ideas about the magnetic field and how particles are transported in the heliosphere.
In 2000, ESA launched Cluster, the first space mission able to study the Earth's space environment in 3 dimensions. It consists of a constellation of 4 identical spacecraft flying information around the Earth. Each satellite is equipped with the same set of scientific instruments that simultaneously measure particles and waves in near-Earth space. The resulting picture, as produced by these 4 spacecraft, can only be achieved using multi-point measurements. Cluster, for the first time, unravels how this environment varies in space and with time. Cluster data have already led to a wealth of new results, and this exciting yield is set to continue.
Just as SOHO observes the Sun and Ulysses the evolution of solar emissions through the interplanetary medium, Cluster captures how the solar wind affects the Earth's magnetosphere. Data from Cluster taken during extreme solar events have shown that the charged particles arrive at the Earth's magnetosphere with a higher speed and greater density than when transported by a regular solar wind. This causes the magnetosphere to be extremely compressed and the Earth's magnetic field lines to oscillate and accelerate particles in the Van Allen radiation belts. Cluster's observations of these phenomena allow us to refine models of our near-Earth environment where commercial and navigation satellites orbit to better predict effects of solar storms on Earth. Another important phenomenon in which data from the Cluster mission have enabled a huge leap forward in understanding is magnetic reconnection. Reconnection is the key mechanism by which the solar wind can penetrate the Earth's magnetic shield, propelling the high-energy solar wind particles towards the Earth. The 4 Cluster spacecraft enabled in particular the first 3-dimensional observation of the heart of the reconnection process. This process occurs across the universe at distances too vast for it to be studied in detail. However, Cluster can study this important phenomenon close up. In 2005, Cluster solved a long-standing problem: why the magnetosphere was found to be constantly topped up with plasma from the solar wind, even though it should have been acting as a barrier to this material. Cluster discovered ejected solar material trapped in large vortex structures, hundreds of thousands of kilometers in size, high above the Earth. These vortices are caused by the fast-moving solar wind sliding past the slower-moving magnetosphere, similar to the process by which waves are whipped up by the wind sliding across the surface of the ocean. It is these vortices that are thought to provide a mechanism for plasma to tunnel its way into the magnetosphere. The high temperature of the solar corona enables matter to escape the sun's gravity as the solar wind. However, it is unclear how the solar wind is heated. Cluster data are helping to piece together the answer to this problem. It has been used to trace how the flow of energy in the solar wind is transferred from very large scales at its source, the corona, to small scales where it is dispersed. This is extremely challenging, and it's a bit like trying to understand how energy is transferred from the calm, smooth flow of a river down to the small, turbulent eddies and foam formed at the bottom of a waterfall. Cluster results showed the importance of electron physics in this process.
The space age made us realize just how fragile our planet is and the intricacy of its relationship with its local star. The complexity of the Sun from its interior to its atmosphere is perplexing. Many or most of the Sun's key physical processes operate on such large scales and over such long time periods that future generations of observations are required to resolve them. Cluster, SOHO and Ulysses allow the investigation of energy flow from the Sun to the Earth and the study of plasma processes in the Earth's magnetosphere driven by the solar wind input. The effect of having a fleet of spacecraft observing our Sun has given us extraordinary insight into the behaviour of a rather ordinary but exceptionally important star, our Sun. I'm Rebecca Barnes. Thank you for watching the Science at ESA vodcast.